Alright, so Module 3, Instruction Set Architecture. So this part is coming from the Computer Organization and Design book, and also Ronald DeMara's slides. Okay. So, in the first session we talked about the compiler and assembler. We mentioned that we have a high-level program like C, and then the compiler compiles it and converts it to something like an assembly program, and then we have an assembler. So today we're going to learn, in this module, we're going to learn how to be a compiler, right? So we have a C code, and you will learn how to convert that to an assembly code. It matters because if you know how it works, then you get a better idea about how a CPU works. Some of these things that we're talking about here is something I personally covered in Intro to Computer Architecture too. So we are still having some overlaps with 212, and I think that's something that we need to do at least for the first few sessions because people come from different backgrounds. I wanted to make sure that everyone has the same background moving to the more advanced topics. That said, we still have some topics that are not discussed in 212, even in this module. Okay, so MIPS. The MIPS instruction set architecture is a load store architecture. So what it means is the only interface between CPU and memory is through load and store instructions. Right? So if you want to add two numbers, we have to load them from memory first, bring them to the register files in CPU, and then we can add them. Right? So what is what other processors have load store architecture? We have RISC-V processor, ARM processors, Spark, PowerPC. These are the processors that are all load store. They have load store instruction set architecture. These types of processors are called RISC. So it's called reduced instruction set computer architectures because we have less number of instructions. We don't have too many instructions. And if you remember, this means something on the hardware implementation too. Because when we have basic instruction, we have the basic instruction in the instruction set architecture. And also to remind you, instruction set architecture is pretty much the vocabulary you have to design an assembly program. So going back to the hardware, when you have basic instruction and instruction set architecture, it means that there is a hardware designed on CPU to take care of that basic instruction. So if you have add instruction, it means that there is an adder in the CPU. If you have a shift instruction, it means there is specific hardware taking care of shift, right? These are basic instructions. So RISC processors, they don't have that many instructions. The instruction set is reduced. It means that the hardware is simpler. Compared to what? Compared to CISC, complex instruction set of computers, which are register memory architectures. The difference here is that you can have instructions that one operand is register, the other one is a memory block. So you don't have to load memory to a register from using one instruction and then add the content. You can directly use an instruction that adds a register with a memory block. Does it mean that we actually have an adder that does that? No. Still the hardware, from the hardware point of view, you still bring the data from memory, you use a register, you add them. But this means that you have just a more flexible instruction. As a user, it's going to be easier. You can call that instruction, you can have a register, add it to something. At the back end, in the hardware, what is going to happen is we go to the memory, we bring it to a register, we call it temporary register, we add them, and so on. It's just a little bit more flexible. That said, they also have more complex processes. So they have more instructions, they might have more complex, they must support more complex computations system. So what we're focusing on in this course is risk. In advanced digital design, we focus on risk. ARM, the R in the ARM company is for risk. So ARM is a company that creates risk processors, or famous for risk processors. Where do we use ARM? IoT, mobile computers, cell phones, right? Okay, so let's talk about the operands in MIPS. One type of operands that we can have in MIPS instructions is register. So we talked about the register file a little bit last time. We mentioned that register file is a small memory that is inside the CPU. There are two design principles. One is smaller designs tend to be faster. So if you have a smaller memory, you have faster memory, probably because it doesn't take that long to access different blocks in the memory. The other one is locality. It's important to have memory close to the processor, right? So this idea of having a register file within the same chip as CPU is based on these two design principles. One is we want to have a small memory instead of having using a cache, which, by the way, might be or might not be in the same chip. Instead of using that has memory, megabyte these days of information, we can have very few memory blocks. In the case of MIPS, we just have 32 registers, that's it. 32 registers. So register files are faster because they are smaller, but also it's because they use a different type of memory technology. It's not just being smaller, but we use a different type of memory technology. We're going to talk about it. And these are located very close to where we do the computation. The entire idea of in-memory computing architectures, by the way, I just had a talk before the class and I have to go to a panel right after this. We're discussing this. The entire idea of in-memory computing architecture is that we want to put them close to each other. So we have near memory computing, that you use very small computing blocks to the memory, so you have a cache, but your cache can just read data. You can do simple computation like multiplication, addition. These kind of computer architectures are designed for modern workloads like machine learning, graph processing. They do a specific task, and they do that specific task, computation, very close to the memory. That's called near memory computing. In-memory computing is even more advanced, and they want to do computation where data exists. So register file is kind of like near memory computing. They bring some of the memory, some part of the memory, but it's a very classic term, so people don't call it near memory computing because it's a very small memory inside CPU, but the idea is the same thing. Let me have a small memory, bring it to the CPU, which is very fast, I can do the computation locally. All right, so although register file is a memory, we don't call it memory. So don't call it memory. Just think about it as a memory, but it's just a register file. Memory, main memory is usually DRAM. We have billions of them, trillions of them. In the main memory, that is something different. And we have cache, which is something different too. We're going to talk about those concepts in the memory hierarchy module. So main memory is optimized for capacity, means that the memory cells that we have are very small. So DRAM is actually very small. We have SRAM. SRAM means 6 transistors. So we use SRAM in cache because it's larger than DRAM, but it's faster than DRAM in some cases, right? So it's like when we talk about the memory hierarchy, that's the idea. We make it smaller, faster, and so on, and physically closer to the CPU. All right. So registers are optimized for speed, not capacity. We're going to talk about what registers are, but they are pretty big in terms of the size. The bit cells, every bit that we store in register needs a bunch of transistors. Now, what are MIPS registers? We mentioned that every register in MIPS has 32 bits. Okay, so we have a dollar sign here. This is showing a register, and we have register 15. and value 7, you see that these bits are 1, 1, 1, and everything else is 0. We have 32 bits registers, even if we don't use them. So with registers, you can't use part of them. You can't say, I just use a byte. You either use the register or don't. You use register T1 or register 15. You can't say use the first half of register 15. Right? But with memory, you can say that. With memory, you can say just load 1 byte. But when it comes to the register, it's 32 bits. It uses the entire 32 bits. We have 32 bits starting from 0 to 31. This is called least significant bit, and this is the most significant bit. And the reason is that this, if we have a 1 here, this is going to be multiplied by 2 to the 0. If we have a 1 here, it's going to be multiplied by 2 to the 31. So it has more significant. What is the actual, if we're getting there, these are some things that you might want to know. When we say word in MIPS, we mean 32 bits. Byte is always a byte. But this is something that you might want to know. Byte is always 8 bits. Okay, but when you use word depends on the processor. You can have an 8-bit processor and 1 word is 1 byte. Then you can have a 32-bit processor and 1 word is 4 bytes. Right, so 32-bit processor, MIPS, it has 4 bytes. Okay, that's something that you want to know. We have microcontrollers that have 8-bit, 1 word in that is 8-bit. We have 64-bit Core i7 processors, 1 word has 64-bit, which is equal to 8 bytes. Okay, byte is always 8 bits, word depends on the processor. Okay, so now, from the software point of view, you move a value to register as a $sign, as I said here, and the 7 is there. High level, look at this graphic, we have 1, 1, 1 stored in these bits, everything else is 0. But what type of technology we use for registers? This is what we have here. This is called flip-flop. So we have, how many of you guys remember flip-flops from digital circuits? So flip-flops are a kind of memory, you can call it a memory cell, that works with a clock. And in one clock, you can read from it and also store something in it. So in the same clock cycle, you can read what was stored in it and store what you want to store in it in the same clock cycle. And it's a pretty fast design. It involves transmission gates, there are different types of flip-flops of course, but every bit in a register is stored in a flip-flop. It's a pretty fast memory cell, but it's a large one. It involves, I think the best design that you can get, probably 12 transistors, I don't remember exactly, but SRAM cells, for example, they need 6 transistors. DRAMs, they have a capacitor that stores the value, and they need refreshing and everything. Okay, so they're pretty big, but they're really fast. They work with the clock, that's why they're called registers. We register to vote. This is the examples that we have. We register for classes. So clock tells when we want to register the input. So we have a clock for register file, and every clock defines when we want to register the input of the flip-flop. So the data is stored, when we clock it, it's going to be sent out. Okay? So I think we covered everything here. Think about the trade-off always. When we go to cache, we're going to have SRAM cells. When we go to main memory, different things. So now let's talk about the register file inputs and outputs. We have 4 inputs for register file and 2 outputs. If we ignore this write control, so we will talk about this later. There's a control signals that control different parts of the CPU. But ignore this for now. We have 4 inputs, 2 outputs. Each register file is 32-bit wide, and we have 32 locations in it. Okay, so you can read 2 values stored in the register file from this register file in one clock cycle. 2 values, contents of 2 registers at the same time. Okay, so that's why we have 2 outputs. when we output the data from register file, it has 32 bits because we are reading the content. Okay. But when we want to address one memory cell, we just need 5 bits. Why? Do you remember from memory the first quiz? First Kahoots that we had?
Because that's like the 32 is 2 to the 5th. So
Yes.
You only need that many to
Exactly.
figure it
So
out.
we have 32 cells. 32 is 2 to the 5, to the 5th, and then we need 5 wires, 5 lines to address 32 memory cells, and that would be enough. So that's why we have 5 bits here, because with 5 bits, we can have numbers from 0 to 31, and that 0 to 31 is the address for each of these blocks in the register file. So the input for that addresses the memory blocks, the registers in the register file, has 5 bits. We also have a destination register file. So this is when we want to write something to the register file. So when we want to read something from it, we have already stored something in it. We want to do an add operation, we want to read. But when we are done with the add, we want to store the result back to the register file. Then you have to address another block again, because you want to define where you want to store the result of addition. So this is going to be stored in another place in the memory, in the register file, and that is called destination address. Destination address needs 5 bits again, because we have 32 cells. But the write data has 32 bits, because we want to write the result of add, for example. The result of add is going to be 32 bits, so when we want to write the content to this registers, we need to have 32 bits, similar to a data bus. This is not a data bus, but it works as a data bus, right? 32 bits. As I mentioned, register files are designed to be fast, but they're not very area efficient. Yeah. Now, with this information about one of the main blocks in CPU, and this is the way we're going to work, by the way. We're going to introduce block by block, and then we're going to put everything together. Okay. So now we have a good idea about what the register file is. Now let's learn a little bit about the MIPS instructions. So this is the instruction set architecture that you're seeing. You can take it from the book. They have the complete list in the book, actually in the books, in both of them, the Patterson and Hennessy Larson. So this is not the complete instruction set architecture, but you can see some of them. We have 5 classes of instructions in MIPS processor. We have arithmetic instructions, add, subtraction, and so on. You have these here. By the way, everything you're seeing in this table is integer operations. We have floating point operations too. We will talk about floating point operations in the floating point module. We have a module just for floating point, so we talk about it then. Here it's just integer operations. We have logical operations like AND, OR, NOR, and we can add and 2 registers and put the results in another register. We have data transfer like load word, store word, load byte, store byte, and so on. So we can see different instructions here. We have branches. Branches are conditional jumps. So you want to jump to another instruction, but you have to check, you want to check a condition first. So these are called branches. They have different types of branches. And then we have unconditional jump. The jump itself, you just jump to an instruction. That's it. Or jump to a label. And then we have jump register and jump and link. Just to test to see if you remember from Intro to Computer Architecture, if you had it, what is jump register and jump and link used for? Probably, even if you take it, don't remember. Go.
I'm just guessing it's like if you had a subroutine and you needed to return with a value or something.
Exactly, yes. So if you have a subroutine procedure function, if you want to jump to there, you generally want to store where you were, and then you get back to where you were. So we're going to talk about these concepts. Don't worry, if you don't remember it, that's one of the reasons that I cover the basics, because if I just go to the processor and you see a jump there, then you just look at me and It's a little bit annoying, so I just want to explain everything again. All right, so now let's start with the MIPS arithmetic instructions. The first instruction we talk about here is an add instruction. But if you know how add works, subtraction is pretty much the same thing. So I don't cover every single instruction. You just have to take it from there. This is add, subtraction is the same story, and so on. So add instruction is literally called add. And then we have two registers which are source registers. This is source 1, and this is source 2, and this is destination register. It is usually the case in MIPS. The source registers are on the right side, the destination registers on the left. We add these two source registers, put the result in the destination. For example, if we want to add A, B, and C and put the result in A, and if we have B and C in register T1 and T2, and A is registered T0, we just put add T0, T1, T2, it adds these two and put the result in T0. Okay. It's the same story for subtraction and everything else. They usually have 3 operands. We have operands or operands. So we have 2 registers, destination registers, and 2 source registers, and 1 destination register. We also have, okay, before jumping there, so can you tell me how many instructions I need to finish to do this? F equal G plus H minus I plus G. We need 3. We need 2 add operations and 1 subtraction. So literally when you're writing the code, you have to have 3 instructions. There's 1 line of the code, and assembly we add S0 and S1, put the result in T0, it's a temporary register. Then we add S3 and S4, put the result in T1, and then we subtract T0 and T1 to S0. Okay, 3 instructions for what you see there. But now the question is, how do we move data to these registers? Because in the beginning everything is 0. So how do we move some content to these registers? And for that we need to talk about the data transfer instructions. So one data transfer instruction that is very useful is called load immediate. Load immediate is used when you want to move a value, like immediate value, to a register. And it's, the instruction for it is LI, load immediate. So when we have load immediate V0 and 4, the content of register V0 is going to change to 4. And it accepts different types of inputs. You can have a decimal integer, you can have hexadecimal, you can have ASCII values. But what is going to be stored in V0, T0, and S1 is binary units. So you can store hexadecimal, but when you actually look at your register, you see binary numbers there, 0s and 1s. Do you remember when I said load immediate or immediate instructions? We talked about it a little bit. When we have immediate instructions, where is this 4 coming from? Okay, go ahead.
It's in the instruction itself.
It is already in the instruction. So when I said load immediate V0 and 4, the 16 bits on the least, now you know the concept of least significant bits. The least significant bits in the instruction itself has the value for 4. Okay? These are the things that we're going to learn slowly. Now we have load immediate T1 3. This is what we just discussed. 3 is not in the memory, it's in the instruction. So this value is coming from the instruction and going directly to a register, which happens to be register T1 in this case. No bit transfers between processor and memory for load immediate. There's another instruction called load address. So this doesn't move the content of the memory to a register. This moves the address for specific content. Right? Just the address. How it is used, you can see with some programs, but for example, when you're working with, like, for example, if you have a search algorithm, you have Word, you want to search for Word, everything is stored in the memory, then you play with the address a little bit more. You go around this address to find the word. Okay? So this is one way we can use it. Okay. next instruction is for registered copying. So I use this instruction to also talk about the concept of pseudo instructions. So pseudo instructions are what is used in assembly for us to better understand, to make it easier for us to program in assembly language. They're not real instructions. It's just for us to better understand it. So there's an equivalent instruction for that. There's an equivalent basic instruction for that. Some pseudo instructions actually combine 2-3 assembly instructions, basic instructions. I keep repeating this. Basic instructions have a hardware CPU for them. Pseudo instructions that just use another hardware. Okay, so now we have move. We're moving one register to another register. We have a source register here to a destination register. That's how it works, from right to left. Okay, we have moved T0, T1. The content of T1 is going to be moved to T0. But this is a pseudo instruction. It's not a real instruction. There's no hardware for move. Okay, so if there's no hardware for move, how can we move a content of one register to another register? How can we do it? Right now you have enough information to give me the answer.
You load register value into memory and then read it back into another register.
So load immediate to a register and move it back. So how do you move that register though? That's the whole idea. How do you go from one register to another register without actually moving?
You add it with 0.
Exactly, yes. So we have add instructions, right? You add one register with 0 and then put the result in another register. Okay, so it's the source register added with register 0. Register 0 is a register that exists in the processor and it can't change its content. Even if you load something to 0, it's going to ignore it. Why? Because it's physically connected to ground, right? Nothing is going to be stored in it. So register 0 is a register that we use to implement this kind of pseudo instructions. You can use it for other reasons too, but one of the important reasons that we use register 0 for is for pseudo instructions. So we have add 0 register source and we put the result in a destination, right? This is a basic instruction. This is not a pseudo instruction. Okay, so now let's talk about program flow control instructions. And we have 2 instructions. We have 2 branches. Branches are conditional jumps. We check a condition. If it's true, we jump. If it is not true, we just go to the next line. This is how assembly works. You have a bunch of instructions. You start from the beginning. When you get to the branches, it checks the condition. If the condition is met, you jump to the label that is inside the branch. If the condition is not met, you just simply go to the next line. Okay, you just ignore that instruction pretty much. We have 2 types of basic instructions for branches. It's called branch equal and branch not equal. We actually have hardware designed in the processor to handle branch equal. Okay. So branch equal compares 2 registers, RT and RS here, for example, RS and RT. And if they're equal, you go to label L1. Every instruction can have a label. When you're programming assembly language, you can have labels for every instruction. And labels are shown by, for example, this is L1, we have L1 colon, and this is a label. So branch not equal is when these 2 registers are not equal, we're going to jump to L1. Okay, it's BNB, branch not equal. No question?
What's the difference with the $RS and RS?
If you have $RS is showing, do I have RS anywhere here? No. So dollar is showing a register. Actually, if you put, okay, we're going to use Mars at some point, and it's just for assembly programming, for you to get some idea. Probably our first project is going to be using Mars to get some idea. If you don't put the $sign, it just doesn't know what it is. Dollar means a register.
Okay, but the explanation in the second one.
So this is, I meant register RS. So this doesn't have $sign, but it's a typo. It was supposed to have a $sign there too. It's register RS and register RT. Yeah, Thank you for pointing it out. The next one is unconditional jump. We just say jump to a label. Okay. Something to keep in mind is that if you don't have branches or jumps in your code, it's just going to run from the first instruction and go all the way to the last one, and that's it. It just stops. We used to work with branches and jumps to move it around in an assembly language. Okay, so now, how can we use these branches, for example? If-else conditions. Go.
Is jump an instruction or a pseudo instruction?
Jump is an actual instruction.
Couldn't you get the same thing with just branch equals 0, 0? Like you compare it, like the values are 0 and 0 or something like that?
Sure, you could do that, yeah.
But I guess
So-
they didn't get
But that's a
convert
design choice, right? So do you wanna have something for jump or not? So like theoretically, you can say you can do subtraction with addition, and that's pretty much a lot of people do, right? So this is just about the bounds. Obviously, you can implement this with branch, but because you might use jump a lot, you just design a dedicated hardware for that. It actually has a different kind of instruction type. So we have an instruction type called J-type, and that's for jump. Right? So that was a design choice in MIPS processor that instead of using branches, they designed a specific hardware to take care of jump. But you could do it, yeah. Okay, now we want to implement an if-else condition by using branches. So usually how we do it is we check a condition. If the condition is met, we do clause 1. If not, we do clause 2. Right? So another way of doing it in MIPS, which is closer to MIPS, is that if this condition is met, go to L1, and in L1 do clause 1. Okay. But if it's not met, it just goes to the next line, which is else. And we do clause 2, and then we jump to L2. Can you explain why we do this go to L2? What would happen if we didn't have this instruction?
It would then execute clause 1 as well.
It would execute clause 1 as well. Because from the MIPS compiler point of view, it just goes to the next instruction. It's your responsibility to move it around in the code. If you don't put the jump, it just says, okay, I execute clause 1, and now I execute clause 2, and then I continue, keep doing it. So you have to put jumps to make sure that you skip those instructions that don't want to run. Okay, now we have the C code. If I is equal to J, F equal G plus H, else F equal G minus H. So what is the assembly code for this?
For the first if, you could just do branch not equals, like I and J, and then you go to the else.
So branch not equal and I and J are T3 and T4. So it means that B and E, T3, T4 go to else. Yes. Right? So if they're not equal, go to else. And what do you do at else? You just use a subtraction, right? You just say sub F is S0. Might as well put it here, why not? So actually it was nice because you said it in a different way, so I want to go for that path and then come back here. So if you check an else, you just do this. But if they're equal, you just go to the next line, and the next line you do G plus H, right? And G plus H is S1 plus S2. Okay, so the way that we have it here is a little bit more straightforward, okay? Straightforward doesn't mean good, right? It's just easy to understand, but it's not good necessarily. So we just simply compare T3 and T4. If they're equal, T3 is I, T4 is J. If they're equal, we jump to true. What we do in true is add G and H, which are S1 and S2, and put the result back in F, which is S0. If it's not true, it means that we have to execute the else clause. and that is subtraction. We subtract S1 and S2, put the result in S0, but then we need to add this jump false here, okay, to skip that instruction. What you said was nice because you didn't need the jump. Think about it a little bit more in the next example. Right? If we check the opposite condition, we don't need the jump. We never mind, just erase it. We need the jump anyways for this example. Forget about it. Next example, we don't need the jump. Okay, so now this was the branch equal and branch not equal. Let's talk about the set less than. So set on less than is another instruction called SLT. And it compares two registers, S1 and S2. And if S1 is less than S2, T0 will be 1. T0 is set to 1. Okay? Just compare two registers, S1 and S2. If S1 is less than S2, T0 is 1. If it is not, T0 is 0. Okay? We can have a variation of that, which is set on less than immediate. We compare it with the number. So S1, if S1 is less than 7, then T0 is 1. If it is not less than 7, T0 is 0. Okay? So now with this information, we can implement other conditions like greater than equal, less than equal, and so on, with the combination of branches and set less than. We don't actually have basic instructions for greater than, smaller than, greater than equal, smaller than equal in MIPS. So this was a design choice. I didn't want to have another hardware to take care of that specifically. What they did was they used a pseudo instruction, like BLT, which is branch less than. And they had BLE, branch less than or equal. BGT, branch greater than, and BGE, branch greater than or equal. Okay? But these are not actual instructions. We don't have hardware for them. These are pseudo instructions that they're using two other instructions. Those two other instructions are set less than and either branch equal or branch not equal. So with the combination of these two, you can realize these other four instructions, assembly instructions that we have. For example, let's start with the first one. And by the way, we use 0 here again, and then register AT. AT is a reserved register. We can use it, but we don't want to use it. Okay, it's not suggested to use these registers. So they're registers like stack pointer, frame pointer, AT. These are the registers that we don't really want to touch when we're programming it, because these are reserved for this kind of things. So what compiler does, every time that we have a BLT, it actually runs two instructions. So static instruction count for this instruction is 2. If I ask about the static instruction count, and if I have BGE, BLE in that instruction, you have to count two basic instructions. What compiler does every time we use BLT, it just converts it to 2 instructions automatically. So now let's see how it works. We have BLT, T1, T2, L. So if T1 is less than T2, we want to go to L. What we can do, we can use set less than instruction. And if T1 is less than T2, then AT is going to be 1. If AT is 1, we want to jump, right? If AT is 1, we want to jump. So because we are working with register 0, we don't have a register 1. And we don't want to work this part. Let me explain. This part is done automatically. Okay, so what it means is that the compiler should use whatever they have to implement this instruction. Compiler has access to register 0. They don't have access to every number in the word. That's the part that you add in your code. When you want to work with 1, 2, 700, 1,000, these are the numbers that you put in your instructions. Compiler doesn't have that access. We don't have register 1. We just have register 0. Because it just has register 0, what it does is that it use branch not equal. So if T1 is less than T2, AT is going to be 1. And if AT is not equal to 0, then it jumps to L. What it means is that when AT is not equal to 0, it means AT is 1. When AT is 1, it means T1 was less than T2. Does that make sense? It can be a little bit confusing, not too much, but did you understand it? It's okay to ask questions. Okay, we do it one more time for BLE, and then for the rest of them we get some idea how it works. So branch less than or equal, we have if T1 is less than or equal T2. Okay? So we don't have less than or equal. We can't use set less than because there's an equal happening there. What is a clever way of solving this problem? We have T1 less than or equal T2. We don't have set less than equal to use here. What can we do? We can use the opposite condition. So we just say, so this is the opposite condition of this if its T2 is less than T1. Right? This is the inverse condition. If T2 is less than T1, is the inverse of this. So now we do this, we see if T2 is less than T1, AT is 1. So if the opposite condition, the inverse condition is met, AT is going to be 1. But when the inverse condition is met, we don't want to jump. Right? We just want to jump if the actual condition is met, not the opposite one. So we use the opposite condition, which is if T2 is less than T1. But because we don't want to jump, we use branch equal, and it doesn't jump if AT is 1. So now let's see what's going to happen. If AT is 1, we're not jumping. And it only happens if T2 is less than T1. If T2 is less than T1, it means that this condition is not met. Now if AT is 0, it means that T2 was not less than T1. And when T2 is not less than T1, it's either greater or equal to T1. So then it actually jumps. All right. So this is how it works. You might want to watch this video a few times to understand how this happened, but it's actually pretty straightforward when you get it. Same story for the other two instructions. Okay, you either use the condition itself or the opposite of that, and you're good. Okay. But what you need to really know is where this slide is. Because you can, after this point, you can just use branch less than equal, branch greater than, BGE, when you want to design a program, and then you simply come back to this slide and replace that BLT with these two instructions. Okay? So, I'm not going to start this because it's too much. But this is an example we're going to start the next session with. Obviously, it's already in the slides. You can take a look at it and see how it works. I'm going to show you 3 different ways that you can do it. With the forward pass, forward way, backward way. The forward way and backward way, we're going to use two instructions. And then at the end, I'm going to show you how we can do this, run this program with just basic instructions. Okay? All right.